Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irfan Syahmi bin Supardi and my matrix number is CE250085. So today I'm going to be presenting the first question of our project, which is a second order circuit, which is a series parallel RLC circuit. So first of all, as you can see, we have a 40 volt source in our circuit. Next, we have a switch which I set the time on 0 second and the time off in 0.1 second. Okay, next is for our resistor. For overdamp case, we need to have omega value higher than alpha value higher than the omega value, which is 100. So we chose 1 kilo ohm to have a higher phi value, and our capacitor, which we have 200 micro. So after simulating, this is the result that we can get from the circuit itself. So theoretically, this huge resistance creates a damping factor of alpha, which is 1000, which is much larger than the omega of our circuit. So on the graph, which is at 100 millisecond, when the switch is off, the voltage will be at 6 volt, which is the same as the VCT that we calculated on our calculation. And after that, we can also see that the current dies out instantly because the resistance chokes it off. However, the voltage takes a very long time to return to zero, nearly a full second after the switch flips. This is called a long tail effect, which is caused by the energy in the capacitor drains out slowly. It doesn't bounce or oscillate at all. Okay, so next is I'm going to be talking about critically damped case. So for this case, we need to have our alpha the same as our omega value. So we chose our resistor value to be 100 ohm so that we can have the same value for both omega and alpha. And our capacitor is the same at 200 microfarad. Okay, so next, after simulating the circuit, we can see that our because of our damping factor is the same with omega, this puts the circuits on the edge. It has enough fraction to stop the oscillation, but not that slow that it slows things down. So the graph proved that at 0.1 second, when the switch operates, the system responds immediately. Unlike the overdamp case, which took long time to settle, here the voltage and the current return to zero in the shortest time possible, roughly around 0.2 seconds later. So you notice that it drops smoothly and stops exactly at zero line without crossing it. There's no ringing and no long tail. This confirms that 100 ohm is the ideal resistance to stabilize this system as fast as possible.
Assalamualaikum and good morning everyone. This is a second order RLC circuit that is specifically designed to be a underdamped. An underdamped state occurs because the resistance in the circuit is low relative to the inductor and capacitor value. When the switch close at 0.1, the 40 volt source suddenly inject energy into the system. Because the circuit is underdamped, the resistor do not provide enough friction to stop the energy immediately. This causes the energy to bounce back and forth between the magnetic field of the inductor and the electric field of the capacitor, creating a temporary ringing effect before it eventually settles. For the graph, visually confirm that the circuit is underdamped through its oscillating waveform. At the 0.1 second mark, instead of the voltage rising smoothly to its final level, it performed a sharp overshoot past the target value. This is followed by several decreasing wave or oscillation, which are the hallmark of an underdamped response. As the resistor slowing dissipate the excess energy as heat, this wave decay until the graph become a flat line. This flat line indicate that the transition phase is over and the circuit has reached its steady state. Okay, we can try to insert the value from the graph to the equation that we get in the calculation to prove the calculation is correct or not. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Adili Fahmi, number matric ACE 250134. I will continue about the question 2 to present our analysis of a sinusoidal steady state circuit. We use specific value for our group. For C1 is 6 millifarad and C2 is 9 millifarad for capacitor, and 0.50 Henry for L1, 0.10 Henry is L2. The circuit is powered by an AC source of 3.46 VRMS at a frequency of 5.30 Hz. This frequency is very low, which is important for how the component behave. The current I0 follow the equation 20 sin in bracket 33.33t minus 45 degree, giving us an angular frequency omega of 33.33 radian per second. Because the frequency is so low, the capacitor have very high reactance and act as the main resistance to the current. Meanwhile, the inductor have low reactance and allow current to pass more easily. Therefore, the capacitor are the boss of this circuit and dictate how the voltage is distributed. We verify this in multisim. As you can see, from the result from the multimeter, confirm the source voltage is exactly 3.46 volt. From the result oscilloscope, show the sine wave of the AC signal with a peak-to-peak voltage of 9.74 volt. The wave is steady, proving the circuit is in a sinusoidal steady state. In summary, our simulation match our theory. The high capacitive impedance at low frequency control the circuit behavior, and our multisim result confirm our nodal analysis calculation are correct. Thank you.